Okay, so we've seen two examples of functions, and now we're going to introduce the formal definition of a function. And basically we're doing this to pull out the important general principles from these examples, which are abundant in everyday life. And once we've done that, we can explore the properties of these functions, which that exploration, if you're going to take calculus, will go on for, all the way through Calc 1 through Calculus 3, and if you become a math major or an engineer, well beyond that. So what are the general principles, what are the unifying principles in these examples? And this basically sums it up. A function is a map or a rule which assigns to each element x of a set A exactly one element called f of x in the set B. Now that f of x we'll discuss below. You could change either the f or the x there, and you would still have a function, but for want of a better name, we'll call the independent variable x here, and the function itself f. How is this apparent in our two previous examples where we had the volume of our glass was pi times h? Well, this says that for any height in a set A, well, what would that set be? Well, the height of the glass must be positive. I would say greater than 0, because a glass with height 0 is not really a glass, although we could get into philosophy here, but let's say h is greater than 0, so the set A here is the set of all h such that h is greater than 0. And where are we sending these values from A? Well, we have a rule, and the rule is that v of h is equal to pi times h. So the rule is that if I pick any one of these values, h greater than 0, I multiply it by pi, and then I should get something in a set B. What would that set B be? It's going to be all values v such that v is in, well, we could say r or r greater than 0. Either one of those would work. So we could say all real numbers are all positive real numbers. This set B is a little more flexible in its definition than the set A. So certainly if I pick any height in this set A, which is all positive real numbers, then I have a rule, that is, I multiply the thing by pi, which gives me a new number in the set B, which is all positive real numbers or all real numbers greater than or equal to 0. So I have a function on my hands here. Here's another example of a function, and quite often we'll talk about functions which look like this, which are polynomials, etc. And we'll lose the application in real life, and this saves us the bother of talking about each application individually or reinventing the wheel whenever we meet a function in real life. So for the most part, when we discuss functions, they're going to look like abstract functions, where our set A is part of the real numbers and our set B is part of the real numbers, and our function is a formula sending one to the other. And the benefits of discussing things abstractly is that you don't have to reinvent the wheel each time you meet a function in real life. Instead, when you recognize the function, you will know the general principles of how functions work and their properties, and you're then free to apply all of those things to the particular function that you've encountered. So here's another example, a little more abstract, of a function. The rule which assigns to each real number its square is a function. How does this relate to this definition? Well, for anything in the set A, which is the set of real numbers, I have a function f of x. And what is that f of x? Well, I can write down a formula for it. This function assigns to each element here, each x from A, its square. So the function applied to x is x squared. So to each x from A, this function assigns the element f of x equal to x squared in B. Now what is B? Well, B can be taken also to be the set of all real numbers, or B could also be chosen to be the set of all real numbers greater than or equal to 0. Either one of those sets would work for a B in this definition. If x is an element of A, x is a real number, then this rule assigns the element f of x equal to x squared in B in the real numbers to x. If x is minus 2 in particular, then f applied, this function applied to minus 2, is minus 2 squared, which is 4. In short, this is a mapper rule which sends x to x squared. So x is in the real numbers, and x squared is in the real numbers. X is in A, x squared is in B, and this rule sends x to x squared. We're going to focus on functions where the set A and B are sets of real numbers. So they might be all of the real numbers or part of the real numbers. And this symbol f of x is going to be read, well, as I have been reading it, as f of x, or f evaluated at x, and it's called the number itself. F of x is the value of f at x, or the image of x under f. So here f of x is x squared. X squared is the image of x under the function f. So this diagram can also include the name of the function, and you have all the information in this diagram. The possible values of x vary, since x can be any element from the set A. So unless the set A has a single element, then these values of x are going to be allowed to vary. And so therefore x is a variable, indicating that its value can vary. And we call it the independent variable, because we can choose what x is. Once we've chosen x, we can't choose its image under f. That's going to be fixed according to the formula or whatever rule we have describing the function. We could replace the symbol x by any other symbol here. So you saw earlier that we had a function v of h equals pi times h, and we had a function d of t equals 60t, and these are rules. And now the independent variable here is h, and the function itself is called v, so we have v is replaced, f is replaced by v, and x is replaced by h in the definition of a function here. So if u denotes our independent variable and d is the name of our function, then the values of the function are denoted by d of u. Or if t denotes our independent variable and d our function, then the values of the function are denoted by d of t. So you can change the names of the independent variable and the function in this definition. The set of numbers to which we apply the function, those are A in the definition, that's called the domain of the function. So for example, our function f of x equals x squared. Here A is everything from minus infinity to infinity, or the real numbers, and this means that the real numbers is the domain of this function. We'll discuss domains in greater detail later. Sometimes the domain is restricted, and sometimes we indicate that, and sometimes we just give the formula, and the domain is everything that fits in the formula. The set of values b, which are equal to f of x, for some x in a, that's called the range of the function. So the range of x is the set of all values f of x for x in a. Now this is different sometimes than the set b. So for example above we had f of x is x squared, and we saw the values of f of x equals x squared. These are always numbers greater than or equal to 0. And also, every positive number is the square of some number, because we can always take its square root, and then it's the square of that positive number. So the range of f here is the set of all real numbers which are greater than or equal to 0. So if f of x equals x squared, then the range is equal to the set of x such that x is greater than or equal to 0, or I might also indicate that in interval format from 0 to infinity, including 0. If we can write our function with a formula, then we can represent it by an equation. So for example, if we can write our function as f of x equals x squared, and we have a formula, a definite formula for our rule, and you'll see later there are other ways of writing functions which are more complicated, then we can represent our function by an equation y equals f of x. And in this case, we would say y equals x squared, and this completely describes what's going on with our function, as long as we understand that y equals f of x. And you see here y is also a variable. Its values vary as x varies, and this is called a dependent variable. X is an independent variable because I can choose it to be any real number, but once I decide what the x should be and put it in the equation, the y is completely determined. I cannot choose what the y will be once I've chosen the x. So y is called the dependent variable because its value depends on the value of x. Now note that writing a function in this way gives us an equation, and we can graph that equation in the Cartesian plane. So this gives us a way to translate from the algebraic definition of a function, the algebraic formula, to a picture in the Cartesian plane, to a geometric object, and we can of course explore the properties of the function either through algebra or through geometry. A good way to think about a function is as a machine or a process that transforms the number you put through it. So if you put in the number x, then the machine works on that x, and then it gives you back a unique number f of x. So for example, if f of x equals x squared, then this is a rule which transforms the x into its square. So you can think of this as a machine, f of x, or f, and you pop this in here. It's like a tree shredder, but it doesn't quite shred the x. Instead, it pops out something interesting. It pops out x squared. So if I feed 4 in here, then I'm going to get 16 out, etc., etc. If I throw a -1 into this machine, I'm going to get a 1 out at the other end. So it's good to think of a function as a machine which transforms the x value you put into it and gives you something new at the other end. Another way to visualize a function as a process is by using an arrow diagram. And here we show an arrow diagram for f of x equals x squared. We have the domain A here on the left, represented with a Venn diagram for a set, and B, the target set, is on the right. And for each point in A, when we apply f of x to it, it gives us a value in B, so we draw an arrow from that point in A to the corresponding value when we apply the function to that value, the value we get in B. So I draw an arrow from -1 in A to 1 in B. This is -1 and this is 1, because when I apply the function to -1, I get the value 1 in B. Now there are a couple of things to keep in mind here. Because I have an exact formula, when I throw any of these x values into the machine, I get a unique x squared out at the other end, a unique value of f of x at the other end. So for every number in A here, there's exactly one arrow leaving from that number. On the other hand, for any number in the range, there must be an arrow coming into it, but there may be two arrows coming into it. So for example, there's an arrow here in this diagram from 1 to 1, because when I apply this function to 1, I get 1. So there are two arrows arriving at 1 in B. Now for some points, say -10 here, there are no arrows arriving at that point, because there is no number whose square is -10. So an element in B can have no arrows, exactly one arrow, such as 0 here, or more than one arrow pointing towards it. If the element is not in the range, there are no arrows arriving at it, because remember, the range has to be f of x for some value of x in A. And in our example, we have two arrows arriving at 4, because f of -2 is 4, and f of 2 is also 4. So the range is the set of values here on the right with at least one arrow arriving at them. And it's important to remember that you must have exactly one arrow leaving every value in A, but you can have more than one arrow arriving at a value in B. What does all of this mean for our example? Or let's just summarize what we know about our example, where our function is the rule which sends any value x from the real numbers to x squared. Well, we can give that function a name, f of x, and we have a formula, a single formula, to express what f of x is. F of x is x squared. You'll see examples where you don't have a single formula below, but in this case we have a single unifying formula describing exactly what our rule is, and that says f of x equals x squared. We can use this formula to calculate the value of the function for any value of x. F of -1 is -1 squared, which is 1. F of 0 is 0 squared, which is 0. And f of 1/2 is 1/2 squared, which is 1/4. What is the domain? Well, this formula applies to all real numbers, so our domain in this case is all real numbers, and that was the A in our definition. And our range is not exactly the B in our definition. B could be anything, but the range is the set of all f of x. And that is the set of all y values, so that y is greater than or equal to 0. So our range is all real numbers greater than or equal to 0. We can represent the function by an equation y equals x squared, and of course we can graph that equation. X is called the independent variable, and it takes any of the values of x in the real numbers, and y is the dependent variable, and its values are going to be in this range. And of course we can draw a graph of this function, which we will do later. When representing a function, there are a number of ways of doing that. We can give a verbal description, as we did with this function. It's the function which sends every real number to its square. We can give an algebraic representation in the form of a formula. Possibly that formula might be a little more complicated than saying f of x is x squared, and we'll get to some examples like that. We can give an equation of the form y equals f of x, and of course we can graph this equation, which gives us a geometric representation of our function. And this is very important and something that you'll explore in great detail in calculus. And we can also use an arrow diagram, as we did above, using Venn diagram with sets. And for the most part in calculus, we're going to use these two representations, the algebraic and the graphical or geometric description of the function. And of course, the Cartesian plane is what allows us to translate the results we get from the algebraic description to a graphical interpretation and vice versa.